Welcome. Come one, come all to an adventure. My name is Jason McGuiness. I've been working in the city of London in finance for 20 years. I've seen most of the most outrageous programming errors and some of the less so. I've seen some of the more curious coding and some of the less so. Here you're going to see some rather curious coding. We're going to have to skip through it a bit because time. But I've basically streamed out. I thought I wanted to focus on the template metaprogramming rather than necessarily the results. So what we're going to do is the results section is a few results, more in the detail. Because frankly, let's go for the pain. We came for template metaprogramming, madness, yes? Let's do it. Okay, right. Template meta-state-machines, Shannon madness, what does this all mean? Well, what happened is I created many years ago a fix to MIT translator. These are two protocols that are used in the city. Fix is a binary pair value protocol, ASCII based, utterly terrible because of course doubles don't round trip in strings. So why on earth would you do this in the city when finance is important and money is important? Madness. Theoretical physicists did it, it's their fault. Stupid. MIT binary based protocol, basically structs. So obviously much better. Of limited sense. Anyway, so what we do is I'm going to have some reflections on what computed-GOTO is, because why? Why computed-GOTO? You see, the point of all this is I decided a while ago I wanted to attempt to create the world's fastest meta-state machine possible using C++. No effort would be spared to save a clock cycle. Hence the madness. But the point is if we've got a computed-GOTO, right, then we've got base plus stride and offset. Well, okay, what about the offset, the multipliers? So these are the hashes. We need to hash some kind of input order type, because we'll send an input order. We've got a state machine. We want to know what it is. Is it a new order, a cancel, a modify, blah, blah, blah. And so we want to hash them. Lots of details. I'm going to go to some methodology, and then we'll have a look at the results, some histograms. I'm quite keen on stats. If you can't measure it, it doesn't exist. My background is maybe theoretical physics, but guilty party, shall we say. But the point is that if you can't measure it, it don't exist. So let's get the stats right. Yes, so I don't run something once and claim it went that fast. That's BS. And anyone who presents such results, I do hope are ashamed. I hope they run it more than 10 times, because 10 times gives you a standard deviation of 10%. Yes? So that means if you want to have a difference in performance, you've got to have about a 20% difference in performance, because of course the two histograms mustn't overlap. Okay? That's what they talk about, the Higgs bosons and 5 nines probability and all that, right? Okay. Why is this so interesting? You see, we've heard about calls before from Robert here, and what you can do with it. By the way, I make no claims for any safety in this code. Remember, performance is paramount. But most of this code runs on hosted servers inside big data centers with large people, burly people stopping you getting in. And you pay lots of money to put your computer there. And there's lots of legalese around it. So we're not really they're not open to the public internet and so forth. So we're not too concerned about buffer overloads, overruns and so forth. Of course, fixed messages, there's great fun, strings and so forth. Anyway, so why are we interested? It's the heart of a state machine. Because a state machine does what's my state, where's my transition? What's my state, where's my transition? And we could implement it with if else. If state is new order, call the new order transition, else, blah, blah, blah. And of course we could do some template meta-programming to unroll that, jolly good. But the point is it's an if-else chain, branch, predictor. Remember, we're all on superscalar processors here, not embedded. I mean, even many embedded processors are superscalar. But branch predictor, fear of the branch predictor. The instruction timing of computed GOTOs are excellent versus mixed prediction of a branch, about 1 or 2 clock cycles versus order 20 for rollback on a superscalar processor for a mispredicted branch. So, you know, hey, I'm looking, can I beat 20 clock cycles? Yeah? Cost of a pipeline restart. So that means is we've got very tight performance constraints. So, we're going to generate these computed GOTOs with absolutely no effort spared. I chose this fixed to MIT translator, basically because it's a fairly large code base, and I've got performance tests before, and blah, 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 because it's there. Computed GOTO versus a naive metastate machine with if-else change, I compared the two. Do I get a performance difference? Is it measurable? The base and stride are actually, we'll leave that to one side because they're relatively easy to compute. It's the state, the input state, new order, cancel order, modify, etc. They're more complex. They may be random because, of course, you know, meat sacks, algos, send orders, right? So as far as I'm concerned, they're effectively random. So we could, in principle, have a preferably minimal hash generated. Of course, Shannon, there's no general solution to this problem. If you give me enough states, I'll give up creating the hash. More on that later. Yes, sounds a bit worrying. Should be. So, I'm going to present results as well. This is very much in terms of kind of a an experiment, method, results, conclusion kind of thing. And I quite like that proposal. Also, it's a bit of an adventure into some wilds. We're going to see some histograms here. I'm going to discuss them. I'm going to give you a subjective review of the code. Obviously, it's not objective because I wrote it. Yeah, maintainability, comprehensibility. Yeah, template metaprogramming. Somebody wrote something about template metaprogramming. Oh, whoopsie, sorry. Was it Kevlin Henny? Henny's maxim, add a template argument, halve the number of programmers who can comprehend the code. Fair enough. Right, so I said state machine sends messages from a client to an exchange, and then we get messages sent back from an exchange to a client. They're both on the hot path, these metastate machines. I created a little simulator to pretend to be an exchange. I don't connect to the LSE or Borsa Italia. I've presented certain areas of this in the past, but as I said, this particular focus is on writing the fastest metastate machine possible, so that I can no longer statistically measure the performance difference with branch prediction or demonstrate I'm better. I want to get to the logical conclusion, the ultimate, the end. Why, oh, why? The mountain was there. Why not climb it? It looks interesting. Keeps me off the streets and annoying grannies. Beware. Yes, premature optimization is the root of all evil. Please, beware. Dijkstra's maxim. Perhaps I'm verging on a few milli-Dijkstra in terms of pretentiousness here, but it's very important to be aware. Run your profiler first. Heed Amdahl's law. Yes? 10% of your code takes 90% of the runtime. Use your profiler first. Do not do this until you've used your profiler and sweated that code. Yes, exactly. This talk obviously fails these two because I've jumped ahead because I already did that and you haven't seen the results of that. Fair enough. Right. So we're going to delve into a few types here. See, type. Constrained override type. Constrained, and it overrides things, and it's a type. Right. So, okay, it's got a closed set. Not open. Why? You see, the runtime state will cause a jump to something called a transition in the process function. We'll call it process, okay? The reason I use process and not the function overload operator, the function call operator, it's easy to grep for process. Hard to grep for parens. Lots of parens in C++. I want to do it in a generic manner. But the problem is the target address is all I know about the destination. Remember, it's a computed-GOTO. It's a jump to an address. There's no type there. It doesn't say, hey, the address has this type, with these parameters. Cool. Remember, it's not an if statement. If state is new order, run the new order transition, pass the parameters in. New order transition dot process open parens, yeah, I know the types. A posteriori. Now I don't. All I know is the target address. So I need to kind of generate something, some wrappers to give me back rather than using void stars. Because obviously we hate void stars. Because we're C++, and why not? It'd be much easier. I tried actually with void star to start with, and I was dissatisfied with that. And I thought I can go better with a little bit of angle brackets. Not a little bit. A lot. This state will index into this collection of transitions because it's a computed-GOTO. By the way, the state machine I've used, it's based, years ago, it was based on Boost.MetaStateMachines. It's kind of morphed into this thing. And you'll see how it's morphed. So, jolly good. We've got this collection, because we've got all these transitions, right? And we need to bung them somewhere into some kind of array, don't we? And obviously, memory allocation is evil. And I want to use the stack everywhere, because of course I don't want to do pointer chasing, because pointer chasing is bad and that'll break that call statement. Because I want, remember, the number of instructions I've got is about 20. I need to be in around 5 to make sure I've got statistical difference, roughly. So, standard array is our friend. I love standard array. There's so many ways you can abuse the poor thing. Yes, you could try and create a structure as a jump table with standard array. I did that. The problem is that's in the data cache and it has to be fetched. And data cache fetches take about 10 clock cycles into a register. Right, I've just burnt half my 20 clock cycles. Bye-bye. So, no, don't do that. Do it another way. So, okay, now you can see how we can compute the base in stride, because, of course, all I do is say, hey, you pass in all these transitions. I find the largest transition, find the appropriate alignment, blah, blah, blah. So there we are, base and offset done. Hand waving over there. Phew. Okay, we want to kind of index into it because we like overloading and, use an index operator so it kind of looks nice. But, of course, we need to pass a parameter, the index parameter, which is, of course, the hashed state. Hello, Mr. Shannon. Hello, entropy. So I'm going to give you a kind of schematic diagram of what these types are before I plunge into them to try and give you a kind of overhead. Okay. A moment. More caffeine. By the way, this is the dead man slot after lunch, so I will be talking loudly, I will be waving my hands, and I will be pointing out to people, okay, to try and keep you awake. Cheers. So, okay. This is my computed-GOTO meta-state machine, instance thereof, or type, if you so will. Right, so we've got state transition table. You want to know about the state transition table, right? So we've got this unordered tuple, I said, which holds all of the transitions. Yeah, their placement nude into there, blah, blah. And then we've got some kind of index operator, and we have a perfect hash, right? But what we do is we have to kind of call a function, don't we? This process function. So we've got to provide it somehow. And remember, all I've got is a pointer, so this sounds like classic OO, doesn't it? So I've got a base class, process method, pure virtual, I inherit from it, and somehow, inherit from the transition as well, and, wunderbar, I can now call the transition process. Brilliant. So this is how we do it. What we do is we go through in our transition, each process overload method, and what we do is we wrap that with an abstract base type process, because what we do is we identify the methods in it, the process methods, and then what we do is iterate over those with template metaprogramming to generate an abstract base class that has that method signature in it as a pure virtual method. And then what we do is daisy chain those all together, inheriting from each other, until we eventually come up with a type called abstract base type that collects them all together. Yay! Cool. So now I've got the pure virtual functions. But the point is, of course, is I now need to actually call the transition process. So now I need some concrete types. Yeah, so what we do is we have this final concrete type that uses the final keyword to finalize everything and get rid of all the virtualization. and more later. And then what we'll do is we'll then call the transition process via the overridden method. Yeah, so what we do is we do this repeatedly. And then what we've got is this type unroller, which goes through the signature types, because of course we've got no reflection, so we need to say a return type and argument types, and then we have a tuple of those, la la la, and we can go through that using our nice template metaprogramming. And then we have the base type, the ultimate base type, because we want to kind of tie everything with a nice little bow. And that's just one row, one transition. More transitions, more of this. N squared algorithm. Yep. Not very quick, eh? Well, fortunately, the number of states we have is relatively small, so that's okay. Phew. Right. So, okay, what's this unordered tuple? The heart of it all. We've got this transition base, right, which is, click, dum, 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 that one. That's collected together, all of those pure virtual functions for a transition. Because, of course, you may have more than one process method, mightn't you? Because we like overloading stuff in C++, don't we? Come on, why not? Hey, we could do it. We're all about genericity, aren't we? So, here we have a max size, which we can compute using all these transitions, you know, size off and all that. Lovely, lovely. By the way, I actually don't use constexpr. I love enums, because enums guarantee it's in the iCache, which means I have no fetch from the data cache and I have less data cache pressure. iCache is also 64K in size rather than 32. Nice. So, blah, we compute the stride. And here we have the index operator, right, where we see we've got some kind of the wrap transitions, we get some kind of base of this collection of transitions, this standard array you see, and then we get a hold of the data, and then we compute an offset into it, right, and then yes, okay, I know reinterpret cast doesn't work in C++, but apparently I've been told that if this doesn't work, I should raise a compiler bug. So I'm okay. Good. Base plus offset. Jolly good. And by the way, yes, I did use standard byte, so technically, yes, that's all fine and dandy. Great. One of those blessed types. Good, good, good. So here we go, as I was saying. Transition base. It's the base class of all transition. The base class of all transitions. Because remember, we've got multiple transitions, right? And I need to call boink. This table, data, that's all of them, right? So now every single transition has to be collected together, and I've got to aggregate together all those abstract base classes into one master abstract base class that is the one that does that reinterpret cast. Because, of course, now you can see, because I've got transition base, I can now call process on it and pass the parameters, because I've recovered the type. There'll be more code later for you to have a look at to see roughly how that's done. So we've got the hashing algorithm. So we turn the state into an index, because the state might be J, B, letters, characters. It might be AF. Not one character, but two. Roughly random. So it's basically unconstrained, and I need to constrain that, obviously. And of course, my transitions have the state and transition pairs, because of course I want to check the state, just to make sure I didn't get it wrong, the hash, right? And then I wrap, each transition, as I said, is wrapped by this constrained overrode type, as you saw from the table earlier, which is contained within the MetaStateMachine, because I make all these things nice and handy for me-ish. And then, of course, these wrap transitions, that's the buffer in which I place them. Obviously, there's a certain amount of placement new, fold expressions, and so forth for the placement deleters as well. Yeah, it gets exciting, the code. Anyway, so if we consider a naive if-else implementation, just to reflect again and help try and get your head around this, right, here we've got my MetaStateMachine process method, yeah? New order comes in, right? I want to pass some parameters. Lovely. So if my state is new order, I'll call the new order transition. But you see, template matching. I know the types here. Great. Blah, blah, blah. Here, on the other hand, you can see there I've done my index. I've got my transitions base. Now I call process. Now you understand the virtualization that's used and the fact that I had to aggregate together all of the transitions and all of their abstract base types, where I generated all the overloads, all the pure virtual functions and all the overrides for all the process methods of each transition. Sorry. I promise you it's only Coca-Cola in there, unless they did something. So you can see here the problem is, this method, the types of these params, I've got to somehow pass them in here, which is why I went to all that funky stuff. Because, of course, now I've got a set of overridden and overloaded process methods in my constrained override type. So this matches. And if you call it with the wrong parameters, it'll buff. Because all the generation from the transitions will say there's no match out of all these overloads. You can imagine the size of the error messages, can't you? Gigabytes. It takes minutes. I've got a 4 gigahertz processor in there. It takes minutes to cut and paste it into a text document. Yeah. Practicality? Anyway, remember I said this is an experiment. It does not need to be practical. So, as I said, if else we know there are types. Here we have to infer the type via the interface class, blah, and it's provided by the base class, tra-la-la-la-la. So here we see, yes, there we are. Right, the big problem is C++ does not support virtual template meta functions. You can't write this. No. Why? Because B tables have to be closed when the translation unit is generated, and that B table is open. So, impossible at the moment. Maybe in the future the Standards Committee will change it. I'm a member of the Standards Committee. I'd probably vote against that. Okay. So as I said, constrained override type, it supplies a base class for each transition with these declarations of the pure virtual process that I got out of it using those signatures types, where I've basically got a using signatures types equals standard tuple of a return type plus standard tuple of the argument types, and repeat those for each method, because we've got no reflection. Yes, it's a bit ugly. There is intrusiveness. Of course there will be. As I said, we aggregate these base classes into an inheritance chain, and we create the wrapper. That's how we can do the process call, and we can guarantee type safety. Pretty cool, huh? So here, for example, I've got my abstract type unroller. Okay. By the way, if you look at the code is more generic than this, so I don't talk about transitions, I talk about thingamabobs. I talked about transitions here because it just makes more sense. Let's specialize a little. So what we can do is we can see here, right, my ultimate base type, as I mentioned, because I want to put a little bow on it, I've got to start from somewhere. Termination's got to stop, right, in generating this, because now if you squint at this, you can see this is essentially, that's the terminal abstract type for each process member function of a transition. And here, I've used the signatures within the transition, right, to generate these functions. And I can pass the parameters as a type to the class, which permits me to have these overloads of virtual functions. And of course, I do the const and non-const, just in case you want to do consty things and so forth, and be nice to you. I like const a lot. So now we go to the abstract type unroller. We need to generate the rest. We've gone to the base, and now if you've got two process methods, well, we're going to have to do it again, aren't we, for the second method. And here we do it for the second method. Look, there's abstract type unroller, recursive calls, and as you can see, a parameter's been dropped, and therefore, of course, we can see termination will occur, is guaranteed to occur eventually. We need to introduce the base process functions to make sure we've not hidden anything, and introduce more methods appropriate to the second process method in the transition. Now, the end result of this, we collect together into here, so that then I can call it easily. And I can give it a relatively easy name that I can type with some sense and not go insane. Yeah, I know my terminology is a little bit, hey, forgive me. So, we need a class that is a transition for which, I mean, Liskos substitutability principle is for which these process functions may be called. So this is why the concrete type appears. Remember, we somehow call the transition. So here you can see it's override, abstract base type, yep. So what we've done is we've overridden a particular method, and there you can see call transition process, because there we are, where is it struck, blah, blah, blah. We've inherited from, where's the colon gone? I can't see the colon. There we go, there. Colon, there, right. We've inherited from the transition and the abstract base types. It's all public, right? So what we've got now is we can then call transition process, forwarding the parameters, because we like to perfect forwarding, attempt to at least. And we can see there's the transition instance thereof. Constructor, of course, can construct it nicely. Non-const, obviously, as well. That was the base type. This, of course, we need to do it recursively, because we've only overridden one of the methods. We need to override the other method in that chain of base types, otherwise it'll say you can't instantiate an abstract object. Fair enough. Same sort of thing, but note here, inherit from concrete type instead. So you can see recursion occurring. This is all, of course, collected together into a finalizer. I just do this simple trick to introduce final, so I can try and get rid of all that virtual function calls, all those virtual function calls, collapse it all. And now you can kind of see that computed-GOTO if you squint really hard, because base, offset, yeah, wink, wink. We're really hoping, of course, that the optimizer does a really good job. Robert, I believe, mentioned about the hopes of optimizers in C++, and the varying degrees our hopes, desires, and wishes are fulfilled. So, final concrete type, that's used by unordered tuple, and it supplies the process method. So yes, as I said, hopefully the final will get rid of all the virtualization, so we'll get the performance, lovely, lovely, and we'll get, you see, all the type information for transition process methods has been recovered by a lot of template angle brackets. We have to introduce this signature types into each transition because of no reflection. You know, I could try, standard has member function. Yeah, what parameters do I use? I don't know, because you might have just decided to make your process method in the transition a template function. This copes. It's all cool, no problem. So here we go, signatures type, and we can see a pair. We've got a return type, remember? Yeah, all the process methods should return the same type. Simplification, so what I do is those are the arguments, that's the assumed return type, and we repeat this for the same return type. Why? It's a state transition table. Process returns the next state, surely. And if it doesn't, you've broken the idea of a state transition table. So I think that's not an unreasonable simplification. The code itself doesn't do that. It's a bit more general. So we can see, I mentioned the meta-state-machine. So here we have the meta-state-machine. And we've got all our states. And we've got what here? Constructor, which somehow makes it. But most interestingly, we've got the process method on it, which there we have table, state, our index operator, hashing occurring, dot process, yeah. That's that virtual call. So now here, look, base, offset, well, base, stride, offset, Likewise for non-const, and there's our table. Obviously, this was a class, this is private, blah, blah, blah. I kept it more simple for explication. None of this code on these screens is guaranteed to compile because of the triple dots that you'll see lurking around. That's the point. If I showed you the real code, it wouldn't fit on a slide. It wouldn't fit on many slides. There are links in the this slide deck to the actual source code. You can have a look at it if you like. The chief item of interest is this state transition table here. You see, because what it's done is it's combined the unordered tuple and the constrained override types to permit that dot to work, and this call to work, and that forwarding to work, these parameter types to match one of the pure virtual methods that we've provided. Of course, we could have a very large V table lurking around, but in principle, Final got rid of it for us. Of course, if you call the wrong transition via a valid but miscomputed hash of state, woe betide you. Because, of course, what I've just done is I've said new order. No, I'm going to call cancel instead. Whoopsie. Whoopsie. Okay, what is this state transition table that I said it collects all these things together? Here we go. We've got the unordered tuple. It's going to need the states, the types of the states it's got, how you index it. It's going to want to know how to call the process method, so that hence the abstract base type, because that's got all those pure virtual methods in it, collected together from all the transitions, from all the process methods in each transition. Then we're going to go perfect hash, right? So we want to get the state from the transition. Remember the transitions in this with the state, right? And I want to get the value of it, and then I want to be able to compute the hash of those types, right? Yeah, compile time too. Cheat warning. Cheat warning. You know, I said collecting together all those abstract base types, all those transitions and so forth. Yeah, I could have done it twice. I got lazy. And I just collected them into the first transition instead. Rather than going across all the transitions, because it turns out most of the transitions have pretty much similar functions, and you can just throw them in the first one and it kind of works. You could do it all again. It's just very boring. And then we've got something called dtuple macros, which is just a meta function that does some magic to turn these transitions and make the row wrapper. You see this row wrapper here, that does all that constrained override type thingy for the signature types, you see, to generate all of those process method overrides and overloads, right? Type, of course. And we do it lots because there's many transitions. So this is how we create our unordered tuple, because we've got all the transitions, bang, 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 right? And it can therefore go, oh, standard array needs to be this big with that alignment, and so on and so forth. So now you can see how I wave my hands with the base and the stride, because I can compute it here relatively easily. I think I just said all this. Yeah, abstract base type done. Hasher, we're going to discuss that in the next section. A meta function, it's not really very clever, the meta function. It just basically does the old apply thing and so on and so forth and tra-la-la. Yes, I know I'm waving my hands. And dtuple macros as well. It does the same sort of thing and generates the constrained override type. It's just how to call it and get all of that template meta-state machinery going. Yeah, you see dtuple macro, constrained override type, result type, just passing the transition. Ta-da, it's that easy. So, okay. What was here? Yes. Here we have, here's our state transition table. You want to declare a state transition table, don't you? So what you want to do is say, for example, we've got a transition, a row, think Boost.MetaStateMachine, another row. These are transitions, right? And we've got a server heartbeat. And what we do is we just send to the client a client heartbeat. And our result is client heartbeat. Ta-da! Now, we get an execution report back from the exchange. An order was filled, an execution report. So what do? We send an execution report response. If we fail to match anything, we've got the match all, and we reject it. Send a reject message to the client. Easy, right? So that's how we get our rows, each row, each transition, to plug into the unordered tuple and the d-tuple macros and the blah, 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 blah. I've omitted the definitions of row and rows for brevity because basically it's just a bit of template. It's a relatively simple template framework. If you're familiar with Boost.MetaStateMachine, you'll be very familiar with that. Okay. The hashing algorithm. Requirements on the hashing algorithm. Right, okay, we've got to move on a bit. How far am I through? Ooh, I don't know. Doesn't say. Where's the page numbers? Oh, trats. Anyway, right. We've got a discrete set of states we know a posteriori, not a priori. We're using prior knowledge. The fact that there are specifications out there that you can download that tell you what the states are. Yes? A posteriori. We make use of that knowledge. We'd like to create a perfect hash, preferably minimal. Why don't I use gperf? Remember, less than 20 instructions. Gperf, too big. Not good enough. Sorry, gperf. You are a very good hash function generator, but you don't quite do what I want. So, we create a hash generator for it, obviously, because we're C++, so we could do these things, can't we? I've got a few simplifications I can do. For example, the hashing needn't be stable in the sense of the order of states. So if I have a state, say, imagine my states are 1, 50, 98. The hash can be not 0, 1, 2, 3, but it could be 3, 2, 1. I don't care. It's okay. It's got to be guaranteed to be collision-free. Collisions are evil, hence perfection is required, preferably minimality. So, after discussing with Dr. Richard Harris, we came up with the idea of the XOR modulo hash. XOR, modulo. Modulo, of course, gives me the minimality, or near minimality. This adds a bit of randomness, a bit of entropy. So then I had to write, because this is rather slow to search through all 2 to the 32 ints, well, unsigned ints, thank you, it takes a little while. So I had to create a parallel algorithm to do it, because it took, well, in release mode, it took about an hour on my lap brick, and that's boring in your build time. So I parallelized it, and I created a data parallel algorithm for this using parallel pixie dust, a parallel data parallel library I have, and it was quite a laugh. Yes, hang on, I'm just trying to create a metastate machine, and now I'm wandering off into creating parallel algorithms. What the heck? Where am I? Stack Overflow? Anybody? Okay, percent operation. You see, as I said, it constrains the output to 0 to the denominator. Yeah, don't worry about percent operator strength reductions, your friend. I checked how minimal the hash shall be. And once we've discovered our seed and our denominator, we can now instantiate, generate a header file which has these in it. And of course, if the seed is 0, yeah, that's optimized out, the XOR. So we can even optimize further. Woohoo, I like optimizations. Optimisations, micro-optimiser. You see, as I said, the problem is that there ain't no such thing as a perfect minimal hash in general, is there? Yeah, the elephant in the room. It does not exist. You give me the right states, and in general, I can't do this. You give me a random collection of states. In general, this will fail. Can't deliver to production. Sorry, boss. We can't handle the new order message because you added a modify to state and we can't do it. Build broken. Practicality, yeah, hello. But remember, this is an experiment. I thought it's an experiment. We're going on an adventure here. How far can we get? So experimentation, denominators must be odd. Even denominators never work. You have to increment it by 1. If you're lucky with an odd set of states, then that's cool. So in other words, minimality is dropped, but we've still got perfection, which is good. Perfection is basically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Incrementing, monotonically incrementing set of digits, natural numbers, including 0. The algorithm that generates searches for the seed in the denominator. It checks for no collisions and won't generate the header file if it gets collisions, because I've got to guarantee that, because unordered tuple has no collision avoidance mechanism. Premature optimization is the root of all evil. Yes. Removed to make it faster. Bad, possibly. Okay, why not let the compiler generate it? Hey, you know, we've all seen what happens with switch statements, yeah? If you have if-else chains, sometimes they get converted into switch statements. And sometimes those switch statements, really funky things happen. And you can even get hashes generated for them. Problem is, these states, whoever invented the MIT protocols was a moron. And I've said this to them. And why did they choose such dumb-ass states? Why did they just choose natural numbers instead? All of this monkeying around, throw away. But no. Thank you, theoretical physicists. Anyway, so compilers are unlikely to generate it for us, which is why we went to all this effort in the first place. Okie dokie. Yep. A bit of detail about my results. Wow, we're doing well. Good. So, what is a fixed to MIT bit translator to people who don't work in the City of London and don't work in finance? How many people here work in finance? How many people have ever heard of fix before? Good, okay. As I mentioned, fix, it's this ASCII format of string value. It's basically, new order is something like, what, 38 equals, tag number 38 equals, blah. Price, tag number 97 equals 9.86753. Yes, doubles are bad, of course. They don't round trip in strings. Right. So what we do is we listen to a client that sends us these fixed format messages. We're going to translate them into these MIT bit format. Bit is Borsa Italia. There's an Italian exchange called Borsa Italia. It's quite large in Europe. And the reason why I didn't choose LSE is BB comes before L. I'm lazy. Alphabetical order. List of them. That one. It was first. Don't care. They're just binary protocols. And I send messages via a server-side socket to my simulator. And what I do is I send a message and receive a message and time it. Okay. I use Boost.ASIO. People go, oh my God, Boost.ASIO is so slow. I've tried to beat Boost.ASIO. Chris Koloff and co did a great job. Deep respect. Very fast for what I use it for, which is basically collect a message and pass it on, collect a message and pass it on. No streaming here. No way. Remember, superscalar processor. That pipeline is God. Or the flying spaghetti monster, and all hail his noodly appendage. Yeah, I didn't use Solarflare open onload drivers. They would have reduced context switches, tra-la-la. I've got some other presentations in the past regarding greater details of how the translator works, if you want more details, and the ugliness. So the test was, I'm going to receive a message, right? Yeah. Oh, and then what happens is we get the message back, right, from the simulator, that's it, and then we're going to respond with a fill from the simulator and translate it back to a fixed fill message. So there's quite a bit of work going on, mainly double to string conversions and string to double conversions, a few string searches, and some copies. The string searches are heavily optimized. The copies are also ridiculously heavily optimized. Yes, I have my own memcopy implementations. And then we send that back to the client. Lovely. The client being, of course, the little bit of program that goes, ping an order, wait for a response, ping an order, wait for a response. My computer was quiescent. Well, my computer was quiescent. I didn't bother to use numeric at all because there's one processor. But I did pin threads, 24 cores. G++ 1310 and Clang 1606. I hate Clang 1606, by the way. And if you ever want to get your code to compile with GCC and Clang, stab your eyes out. Yeah. Everyone, oh yeah, I'll compile it with both compilers. Yeah. Last night I had to rip out ranges because Clang won't compile GCC's implementation of ranges. Just says no. Bye-bye ranges. Right, yeah, I'm a grade A, type 1 personality, Gen 2 Linux, custom ABI. Yes, I do use all the command line options in my make.conf. Yep, I do use regparam and all of that. So in fact, the ABI on there is non-standard to be faster. Save those clock cycles. Yeah, Ryzen 9 3900. DDR4 RAM, 64 gigs. 2 cards, of course. Always 2 cards. Why? Pipeline fetches. Me like. NVMe storage. I love NVMe storage. The NVMe drives in these are as fast as the DDR4 RAM. You don't notice paging, apart from when the processor goes into overload mode and stop clock. When it gets too hot. Thermal dissipation is a problem. It slows down when it gets too hot. And that's nothing to do with C states. You could turn off the C states, it's still going to slow itself down because of electron migration in the processor. Right. So, what I'm going to do is in my tests, right, I had a look at the assembly because I thought, how far did I get? Well, I've omitted the assembly because we've only got finite time here. The assembly is available online. You can try and use objdump. Godbolt failed. It's a bit unfair on poor Matt to cut and paste about, 100,000 lines of hideous template meta-programming into his website and hope it'll, generate stuff, whilst the poor thing takes about 10 minutes to compile on that. Yeah. I don't wish to cause him that much pain and then get nasty emails from him saying, please cease and desist, you Mr. Dosser, you. The code generation was poor. Lots of LEA instructions. What are LEA instructions? It's probably, these LEAs were probably creating address generation interlocks. Address generation interlocks, if you happen to know the x86 architecture, are to be feared. They are hell. Why? Because what you've done is you've just overloaded your pipeline. What you've said is that address computer. Right, okay. Pipelines and superscalar processors. When I do instruction fetch, and I do an instruction fetch on the call instruction or a jump instruction, the multiply and the add exist in the fetch stage. There's actually adders and multipliers put in there. It takes lots of transistors. They run in one clock cycle. Holy moly! You could multiply in one clock cycle? Yeah, ripple carry add. Yeah. Takes lots and 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 lots of chained adders. And that's what they put in there. And that's why you've got, a trillion transistors in these chips, right? And that's why they run so hot. So what you can do is, if you're really lucky, and those, the multiply and the add, you can make them, you can put them into either they're already fetched into a register, and they're the right registers, because register spill is a problem, and also, better still, immediates. And that's why I was paranoid about the immediates. Because if I can put immediates in there, I'm more likely to avoid an address generation interlock. Because what happens is that you don't use the bit at instruction fetch. You have to wait until it gets issued to the pipeline, and then you take up an adder, and you have to wait for the result for the adder. So you do a multiply, and then you have to wait for the result for the multiply. Yes, there are bypass buses on x86, Intel, and AMD implementations of x86 32 and 64, which will route it faster to the adder that you need. But the problem is that the result still occurs pretty much at the end of the pipeline. It takes about 10 clock cycles just to compute the target. And I've got less than 20 clock cycles. Ouch! Code generation was poor. Yeah, an objdump was terrible. Really, you don't want to look at objdump in this. It takes about half a day of editing the output to try and work out what the hell's going on. Okay, here's some results. Okay, what is mean average deviation? Mad. Some people call me it. Yes, I agree. 5% mean average deviation, it's similar to standard deviation, apart from there's no 1 over root n factor, so it doesn't damp, so it takes much longer for it to converge. You use it because that's not a standard deviation, a normal distribution, is it? Right? Where's the normal distribution? Well, it doesn't even go negative, for starters, right? Because you don't get negative latencies, do you? Well, not unless you break the speed of tachyons and so forth. And if you've got negative latencies, frankly, that means you can stiff the city, right? Because you have prior knowledge. Marvelous. And of course, insider trading is illegal. So no, we can't have negative latencies. More like a Poisson distribution, but it's not even like a Poisson distribution. I mean, I suppose you can have sort of thing. But, oh, yes, and right. Histograms, yes, there's my residual. Yeah. So you can see these are the outliers collected into this last bucket, because I don't lie in my histograms like many people. And I'm also very careful to get my bucket size right so I don't get harmonics between the peaks and the actual sampling to avoid Nyquist issues. We can see, what's this? GCC, if else, and computed-GOTO. Right, so computed-GOTO is the kind of purpley color, and the other one's if else. And if we squint at it, they look pretty much the same. I mean, look, there's the standard deviations that GNU plot estimated, and it even thought that the standard deviation for the if else was better. But if we look at this and squint a bit, because remember, the histograms is what it's all about. The standard deviation and the mean or mode it's just all it is a shorthand for the histogram. It's all about the histogram. Here, if we look at it and squint, it looks like our computed-GOTO managed to beat approximately 30 years of research in branch prediction in that Ryzen 3900 AMD processor, of which AMD were pretty proud of when they produced it. Yeah, their branch prediction is about 96 to 97% accurate. They're very, very quiet about accuracy rates on branch predictors because it's absolutely key. I mean, if my branch predictor is 0.1% better than yours, I can beat you in a data center. I've got the market. It's absolutely key. It's very proprietary. Latencies, obviously, slower that way. Binning, yes. 10 to the 14. Sorry, 10 to the 7. That's over 10 million orders sent. Yeah, there's a lot. Hours on this. You don't generate these results quickly. But we can see, yeah, despite the curious assembly generated and the fact that GCC is a bit regarding its code generation, yeah, we kind of got better. We're certainly hitting the noise floor, which is what I aimed to do. I aimed to get as close as possible, if not beat, branch prediction. Here, might have even got faster, and it might be just the optimizer in GCC that's failing me because of the poorer code generation. Okay, how about Clang? Right, me and Clang and GCC, if you know me from history, we've had a bit of a kind of bouncing around because Clang, in the past, used to generate code that was about 20 to 30% slower than GCC. So if you wanted to speed up your code, just compile it with GCC and it'll be faster. Way. But then back in the day, GCC decided, you know what, we don't like this, poor Clang. So they slowed down their code generation by about 20%, generated code by about 20%, Clang sped up by about 10%. So now they're about the same speed. Yeah, 20% slower than they were. Don't tell your bosses. Older compilers are faster. I've got other graphs where it shows canonical decrease in performance. If you want to go for the fastest performance, GCC 4.1. Yeah. Yeah, it'll run twice the speed. Generated code will be about twice as fast. Go to GC 4.1. Throw away all that garbage. Standards committee, 3-year cadence. Maybe the poor programmers who write the compilers don't have time to implement it properly and optimize it all and smooth it and make it all pretty and put a bow on it because we keep on shoving new stuff at them. Just saying. So, Clang, how did you do? You see, my convergences are pretty good, actually. 5%, 4%. This is actually statistically significant, this stuff. Again, massive numbers of orders. We look at the outliers. Fewer, but higher. Yeah, order of magnitude higher than the outliers. Clang seems to beat its if-else code generation seems to be better than the computed-GOTO. So again, depends on your compiler. Don't trust your performance figures unless you really know what you're doing. You've got to have a lot of test cases for this, because remember, what you're doing is removing instructions to go faster. Removing instructions means you're not doing stuff. Now, that stuff may be irrelevant. Maybe it's really, really important and you just broke a test case. Maybe you just broke the test case that said the cancel message will work. Why is a cancel message important? Fat finger? Whoopsie, I just said I'm going to buy 100 million shares of IBM for $1 million each. Hello, Night Capital. Yeah? You really want to be able to send out a cancel message very fast. Please. So performance is critical and knowing your test cases is vital. Number of samples is vital. These resonances here that we see at about 1 microsecond intervals, that's roughly going to be about what? 1,000 clock cycles, 1,000 instructions, right? Odd. A friend of mine, Vlad, suggested it might actually be to do with, I use SSE instructions for my mem copies and searches in strings. And what happens in modern processors is commonly the vector unit is actually underclocked, powered down, because it consumes so many resources. And heat dissipation, so it's not always powered on. So when you start to do a MMX instruction, SSE, SSE4, whatever, blah, 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 right, what it does is it has to go, hang on, power it up, wind up the rubber band, brum, off we go. And so you get pauses. It's possible. The reason I use them is because I want to get off the integer pipelines in the precious core and use those for the things that are really important to spread the heat out so I don't get thermal dissipation maxima effects in certain areas of the pipeline that cause it to underclock. Micro-optimisation by heat dissipation. You heard it here first. So, very small improvements. We've hit the noise floor. That's what I wanted to do. Remember, my experiment was to go as fast as possible and try and beat if-else. And I've got some evidence to demonstrate that is certainly possible. Because I used the same input states, my branch predictor was hot. Burning hot. So it wasn't taking 20 clock cycles, it was just going bang. So I was going for literally the most conservative, hardest to beat case. And I nearly beat it. Little old me. Hi, Intel. Hi, AMD. Hi. Just saying. Yeah. Yeah, object dump had issues generated. The compilers, she was compiling the code. On Monday night, it wouldn't compile. Despite the fact the day before it did. A good stiff cleaning with CMake and so forth. Sorted that out. Constrained override type. Abstract base type. Yeah? Unordered tuple. Generating a hash that may not even ever exist. Really? Template metaprogramming? Maintainability is lost, isn't it? No, not very well. Magically, mystically, godlike well. You cannot trust the compiler. Sometimes it compiles, sometimes it doesn't. The compile time, by adding all this lovely, interesting code, was not significantly increased, bizarrely, because, of course, the compile times are so much longer because of all the other stuff I did. Less powerful computers. I have one poor computer, and it takes about half a day to compile the code. Not exactly practical. Yeah, 10 gigs of RAM per translation unit. So yeah, I know, I'll use -J. Yeah, and page. Bye. I'll connect to the computer next week. Yeah, limits the parallelization of the build. If you've got 60 gigs of RAM, that's -J6. No space for the OS, no space for anything else. Back away from the keyboard. Yeah, CMake build scripts. Yes, let's compile some code to generate a header file that's this library is dependent on. You see, you've got to generate the hash function first, because that's a header file, isn't it? Which means I can't go compiling any part of the library until I've got the hash function generated. All stop, please, for the hash function. All because they couldn't be bothered to use 0, 1, 2, 3, 4, 5 in the specs for MIT. All those geniuses, yeah? Really? Geniuses? Hello? Sorry. I now work for a different company, so I can get away with this, and I've always done it anyway. Yeah, really, should you rely on luck to compile your code? Really? Standard hash, Psi, Murmur2, far too slow. I do have other slides on performance of hash functions, obviously. I even have slides on performance of how to measure time. Yeah, and which is what better instructions to use. Did you notice it said in order for the timing? Yeah. That's RDTS, CPU ID, RDTSC at the start, which can serialize the processor, and then at the end of it, RDTSCP. That's the canonical way to do it. Okay? Got that, people? Good. Right? You don't use RDTSC unless you prefix it with CPU ID to serialize your processor. I've also got performance tests of the relative performance of measuring just using RDTSC versus doing it the correct way, out of order versus in order, and there is actually a difference in the performance measurement, but there's no statistically significant difference in cost to performance. Given these slides and the fact that I think I've now demonstrated I am an insane, mad micro-optimiser, what was it? Madness? Template metaprogramming? Madness, yes. Perhaps I've demonstrated via hand waving, and there are slides elsewhere, have a look, and which will demonstrate this. Also, currently, I've got less than or equal to 7 states. So I managed in every case to generate the hash function. Yeah. Sort of. One of the cases it failed. Yeah, that was only with 4. Just the numbers were wrong. So I added an extra state, and then it worked. Exorbitant effort to achieve little result? Yeah, well, okay, you could argue that. But that wasn't the experiment. That's an outcome and an observation of it. The experiment was, remember, no effort shall be spared to try and achieve the fastest metastate machine that is possible with C++ without descending into assembler. There were talks about that with people, and I thought hard along those lines, and I thought, no, I'm going to constrain myself to C++ here. Why? Maybe I like angle brackets too much. Because the mountain was there to be climbed. I think it's not unreasonable to say that heroic effort was required. And perhaps I'm getting to, perhaps 10 milli-Dijkstra there in pretentiousness, but hey, look, I'm wearing a t-shirt like this. Come on. heroic effort, but we did manage to recover the type information with minimal intrusiveness. Would I say immediately run off and go and use constrained override type? Yeah. Consider your use case very carefully and your career very carefully, and your compile times and life. Having to attempt to implement a data parallel algorithm and prove that the data parallel algorithm will terminate is correct, tra-la-la, will load balance correctly and so forth. Yep, early out reasonably and so on, not crash. I managed to find a bug that existed for 10 years in my atomic shared pointer. Why do I have an atomic shared pointer? Because I've got a singly linked list that's atomic. And how do I get around the ABA problem? Reference count. I don't have a retire list, I reference count instead. So therefore I need an atomic shared pointer. And when I say it's atomic, if two threads take a reference to the same shared pointer, this is absolutely fine. They can both reset or assign randomly as they desire, and it will work. Don't do it. Don't write that shared pointer. It's slower than a normal shared pointer. Trust me, I've got the performance test for it to demonstrate it. Other talks. But we have got a blisteringly fast template meta-programmed MetaStateMachine implemented as a library for your delectation. Choice of micro-optimisations investigating is vital. Premature optimization is the root of all evil. This is premature optimization. Make no bones about it. Hopefully the techniques here will serve as a warning to others. Maybe you should think about going this far. Maybe not. Maybe you should just, C's good enough. Perhaps Rust. I did it so you would not have to. Yeah? Somebody says to you, hey, MetaStateMachines, let's go for it, man. You can go, look at this. We don't have to. He's done it and sweated for us. And finally, I know I've overrun a smidge. I apologize. My sincere thanks to John Chesterfield, who listened to me talk about this since 2017. He was saying, why not just use assembler? I think yes. Most Chief Paul Evans and Vlad for reviewing these slides, who I'm most sincerely grateful for too. For any more information, methodology, etc., there's my email. The slides will be given to the NDC Techtown, so you can get them. And I have a number of references, as you can see. So we'll leave it there. I know I've overrun slightly. I do apologize about 9 minutes. Hopefully we have time for a few questions. Otherwise, tea and coffee awaits.